As we saw in our previous class, by using transistors as electronic switches, we could implement logic and also store bits of information. We could store either a 0 or a 1. But is that it? Can't we store bigger numbers on a computer? You definitely know that it is possible, but my question to you is how? As a hint, try to correlate this with numbers that we use daily, wherein we have digits only from 0 to 9. So here's what we do in our daily life. We club digits together to form bigger numbers. Simple, right? For example, let's say we want to say 129. So we would write it as 1, 2, 9. One thing to notice over here is at every position in this number, we assign weights. That is, we multiply this number by 1, this by 10, this by 100, and so on. That is, you could write 129 as 1 into 100 plus 2 times 10 plus 9 times 1. That is 1 times 10 raised to 2 plus 2 times 10 raised to 1 plus 9 times 10 raised to 0. This form of representing the numbers wherein we have weights in the powers of 10 is called the decimal number system, which comes from the Greek word deca, which means 10. So in our daily life, when we use 10 digits from 0 to 9, it becomes convenient for us to use a number system with powers of 10. But in the world of computers, we only have either a 0 or a 1. So it makes sense to use and represent numbers in the power of 2. So in the world of computers, let's see how will you represent something such as a number 7. We already saw that we'll be using powers of 2 over here. So what should we put in these brackets so that it represents the number 7? So let's try to figure this out. 2 raised to 2 is 4, and to get to this number we need at least 4 plus, I'm looking for another 2 at least, yes, so I would add a 1, multiply it by 1, and I'm looking for another 1 now, and 2 raised to 0 is 1, so I need that as well. So this will give me number 7. This form of representing the numbers in the powers of 2 is what we call as the binary number system. Therefore, 7 in our decimal number system is equal to 1, 1, another 1 in binary form. So here's your quiz. Convert the number 11 in decimal to its binary equivalent. Here's the solution. For number 11, we want to start with at least 2 to the power 3, which will give us 8, and so on until 2 to the power 0, which will give us 1. So, do we need 8 to get to 11? Yes, we need it. Plus 4, but that will get us to 12. We don't want 4. Do we need 2? Yes, we need another 2 at least. That got us to 10. Do we need another 1? Yes, we do. So 11 to the base 10 is 1, 0, 1, 1 to the base 2. So let's do another example to make sure that you get the concept. Convert 15 to the base 10, which is the decimal, to its equivalent binary form. Here's how you would solve it. To get to 15, we must start with at least 2 to the power 3. which is 8. If we go to 2 to the power 4, that will be 16, that will be too high. So let's start with 2 to the power 3 and go all the way to 2 to the power 0, which is 1. So do we need the 8? Yes, we do. Do we need 4 this time? Yes, we need 4, so that gets us to 12. Do we need another 2? Yes, we still do, at least 2 more, which got us to 14. And do we need another 1 at least? Yes, we need the 1 as well, which will get us to 15. Therefore, 15 to the base 10 is equal to 1, 1, 1 and another 1 in binary form.